Good morning. Today, let's investigate about spatial multiplexing. So the main use of spatial multiplexing in MIMO wireless communication system is that this guy increases data rate in MIMO communication system. How spatial multiplexing can increase data rate and what spatial multiplexing is, let's study now. See, okay, spatial multiplexing in multi-input, multi-output wireless communication system. So when we say multi-input means multiple transmit or multiple transmitter antennas, and MO indicates multiple receiver antennas. Okay, so this spatial multiplexing MIMO, so this quantity increases data rate in our wireless communication system. How come? For example, let's go to a spatial diversity. Okay, if we take spatial diversity, let's take a transmitter case. Okay, this is my transmitter, and let's take, say, you have two antennas here, say transmit antenna 1, transmit antenna 2, and okay, let's also take a receiver antenna, receiver section. So you have receiver antenna R1, receiver antenna R2. Now say at the input you have two symbols. Okay, say symbol 1 and say symbol 2. You know very well, symbol is a group of bits. Okay, say 2 bits, 3, 4, so on like that. So I have a couple of symbols, S1 and S2. Now if it is a spatial diversity scheme, what happens is that now see transmitter antenna 1. So this guy is transmitting symbol S1. Transmitter antenna 2 also transmits same symbol S1. Okay, over multiple paths available. So in this case, we have, say, 4 paths because we have 2x2 MIMO. All right, so this is one path, one wireless path. Okay, radio path otherwise. This is another path you have. And this is, okay, let's take another color. This is, okay, the other paths we have here. All right, so you have total 4 paths, and over these 4 paths, same symbol S1 will be transmitted. Say, for example, if this path, and say if this path is in deep fade, okay, now you can't transmit symbols over these 2 paths now, so you can transmit symbols over these 2 paths here. So at the receiver side, we can collect these 2 symbols. That means you'll be having good energy so that you can recognize your symbol at the receiver side. Okay, of course, and we know very well that diversity will improve. Diversity, it improves reliability. Yeah, because it is combating, diversity is combating the fading problem. Okay, so therefore you'll be having a successful transmission, so that you can say that you have good reliability. So when reliability is good, that means you have good signal to noise ratio at the receiver end. So with diversity, we can achieve good reliability and hence SNR. So what can we achieve with this? Spatial multiplexing. Okay, so in diversity, what we observed also is that you are transmitting same symbols across various paths. Okay, but in case of spatial multiplexing, the beauty is this. Okay, let me take in a simple language. You have spatial multiplexing block. Okay, and let's take again two antennas. Okay, I have transmit antenna 1, transmit antenna 2. Let me take again, I have two symbols in Q. So symbols are arriving at a faster rate at the input side. So we can demultiplex these two symbols for these two antennas at a lower rate. Okay, anyways, so this is S1, S2 symbols you have, and okay, you are inputting these two symbols. Now, this spatial multiplexing, the beauty is that, so this transmitter antenna 1, this guy will transmit symbol 1, and now T2 will transmit symbol 2, S2. Now see, over same bandwidth, initially you're transmitting a single symbol, but in this case, you're transmitting two symbols. So parallelly, we are transmitting two symbols over same bandwidth. So this indicates that you have high data rate when compared to the previous scheme. Okay, so that's the beauty of this spatial multiplexing, because you are, in this case, you are multiplexing the RF channel. You are not multiplexing in time or in frequency. Rather, you're multiplexing the space. See, engineers, they don't leave anything. Okay, so even we are not leaving the space also. So we are trying to utilize the existing space. We are multiplexing the space. When I say space, the RF channel, okay, the wireless channel. So you are multiplexing the wireless channel here. So, and also you're transmitting different symbols parallelly using different transmitter antennas. Okay, so and that's the main goal of spatial multiplexing. Okay, now let's make it a system. Okay, let's take a schematic like this. Say right, say let's go into this system, say spatial multiplexing encoder. All right, and say you have, as usual, I'm just taking for simplicity only two antennas. Okay, and this is, so this is say spatial multiplexing detector. All right, and again I take here two antennas. It may not be always same number of antennas at transmit and receiver. You can take different values. So okay, anyways, so I have T1, T2, and I have receiver antenna 1, receiver antenna 2. Okay, now say you have at the input, data symbols are coming at high rate. So say this is a symbol 1. Yeah, so symbol 1, say you have some 4 bits for S1, 4 binary bits, and let's take again some 4 bits as symbol 2. Okay, so as we know very well, say, okay, let's assume like this. So transmitter antenna 1 is taking responsibility in transmitting the symbol S1, and transmitter antenna 2 is taking responsibility in transmitting symbol S2. Okay, so how many, how many are radio paths we have in this case? As we know, we have 4 radio paths available. Let's take this color. Okay, so okay, so I have path 1, I have path 2. All right, and I have, say, path 3 and path 4. All right, and say the Rayleigh channel fading coefficient of this path is say H11, and this is say this is say like H21, and this one is say H12, okay, and this is H22. So our channel matrix is ready. So our channel matrix is comprising of four Rayleigh fading channel coefficients, H11 all the way to H22. Okay, so now we have a transmit symbol vector. So our transmit symbol vector is what? S1 and S2. Okay, so let me write. So you have transmit symbol vector. Let's label this one as say yes. Okay, this quantity is say yes. S is, you have a vector of two symbols. Okay, we are transmitting two different symbols using two different transmitter antennas. And also let's say you have channel matrix, you have radio channel, RF channel matrix. See, you're multiplexing the channel. Okay, you're multiplexing the space. That's the beauty. So therefore you're transmitting symbols individually without any interference. Okay, because you have certain spacing, you know, between antennas. So therefore you can achieve that individual simultaneous transmissions over same bandwidth. Okay, so again, the beauty of this spatial multiplexing is that you are not using extra power to transmit different symbols, and also you're not using any extra bandwidth. Okay, so you can say no extra power, no extra power, and no extra bandwidth. Okay, so over same bandwidth you're transmitting different symbols. So this is what improving the spectrum efficiency. Okay, so spectrum efficiency can be improved with this spatial multiplexing concept. Anyways, in general, for example, if you want to improve data rate, and that is possible over high bandwidth. All right, so okay, let's go to that and again come back. Okay, so if I want to improve bandwidth, I mean improve data rates, I want this improve data rate or faster transmission, I mean to say, and this is possible at high bandwidths. So we require high bandwidths for this, but high bandwidth is really costly, it's expensive. Okay, now can I transmit, okay, say can I achieve high data rates at fixed bandwidth? To a certain extent, yes, it is possible, and that's what this spatial multiplexing is talking about. You're fixing the bandwidth, but you're improving the data rate, and this is because of what? Multiple antennas. When we take multiple antennas, now you have a chance of multiplexing the space, and then you're transmitting different symbols individually without any kind of interference. Okay, so you have multiple antennas both at transmitter and receiver. So because of this, you have a chance of transmitting symbols, okay, parallelly. See, when we say, whenever you encounter the word you're transmitting, I mean, you can achieve parallel transmission. It doesn't mean that, see, the paths here we have like H11, H22. No, this is not the intention. Okay, parallel transmission means you're transmitting symbols, different symbols parallelly. Okay, that's it. So now, anyways, so we understood that with the help of multiple antennas over fixed bandwidth, we can improve data rate. Okay, it doesn't mean that our low bandwidth, if I go for infinite number of antennas, I can achieve high data rates. No, there is always a practical limit. You can't go beyond that. Okay. Anyways, we will go to that jargon in our subsequent lectures, not now. So for now, let's model this spatial multiplexing stuff. Okay, so our channel matrix is what, say H. Let's take our channel matrix as H. Okay, this is transmit symbol vector as S, channel matrix as H. So H is nothing but you have 4 fading coefficients. So I'm taking row wise. Row corresponds to receiver antennas, column corresponds to transmitter antennas. Okay, that we'll see. All right, and again you have received samples or received symbols. Okay, so you're transmitting these two symbols, S1, S2, through this channel of you have some fading coefficients here, H1 to H2, and at the receiver side, say we obtained these two symbols. I transmitted S1 and say I received R1. We transmitted symbol S2, say we received symbol R2. Okay. Now what we can do is you can make use of detection methods, okay, using which you can make an estimate for R1 and R2 for S1 and S2 respectively. That means, okay, so that means, okay, before we go there, let's see, let's just write down this received symbol vector or receiver symbol vector. Let's take R. So R is equal to R1 and R2. And let's take additive white Gaussian noise at the receiving end. So you have noise. Okay, I take additive white Gaussian noise with mean at 0 and variance, variance as sigma square. So this noise, I'll take it as a vector again, noise vector. I have 2 receiver antennas. So therefore 2 components for noise, N1 and N2. Okay, so you can model this. You can model this stuff something like this. All right. So yeah, so I have a channel matrix. You have a channel matrix H11. I'm see H11 here, H12, H21, H22. Now you are transforming your symbol vector, your transmit symbol vector, say S1, S2 to a received symbol vector. So you're transforming one form of vector to other form using this, using this channel matrix. So that means you are pumping 2 symbols into the channel, and output of the channel you are seeing these 2 symbols R1, R2. All right, and of course you have additive white Gaussian noise and 1 and 2. All right, so in simple words, so this is nothing but R is equal to channel matrix H multiplied by symbol vector, say plus this noise vector. Okay, so now the order is simple. So how many the order is, you have 2 rows and 1 column. Okay, I have 2 rows here and 1 column, and so, and also I have yes as 2 by 1. So this H must be of course 2 by 2, as you have that, and of course this must be again 2 by 1. All right, so this is a simple model for this. All right, so now you can say, for example, Now I want to go for detection purpose. So I'm in a detection. Now I can make, there are several methods currently in use for detection processing, and say one of those methods, okay, say those methods maybe, okay, let me put it down like this. Say you have one of the methods as maximum likelihood method. So I use this at this block, say, and also you have, must be knowing about this, because zero forcing method, and also we have minimum mean square error, and also you have successive interference cancellation, and also you have ordered successive interference cancellation, and so on. Okay, anyways, you say we make use of zero forcing method, okay, and say we made an estimation, say for this R2 as S2 cap and R1 to say S1 cap. Now we have to see to that the error between this estimation S2 cap and this S2 should be as low as possible. Similarly, the error between S1 cap and S1 should be as low as possible, and that depends upon these methods you have, like max likelihood, zero forcing, and MMSC, SIC, so on like that. So okay, so that depends upon the method, and we can make use of that. So in our course, what we do is we will try to employ these two, zero forcing technique and the basic MMSC technique. Okay, so using this, how can we make an estimation for the received symbols? Okay, so that will be our subsequent, maybe our next class or subsequent lectures, you can see to that. So this is all about spatial multiplexing for now. Okay, if you have any questions to ask, you can put down in the comment box so that I'll try to address them out. Okay, so thank you